Hey guys, today we're going to bring all of our solving trig equations together. And again, this is just some extra help if you needed some ideas for strategies to use when you're just looking at a bunch of trig equations and you're asking where do you start. So there are actually 4 different types of solving trig equations. And you can see it on your graphic organizer. And you can solve by square roots, by combining like terms, by factoring, and there's 2 different types of factoring, and then by using some of the trig identities that are on our formula chart. So let's start by talking about the square roots way. Okay, so when I am solving by square roots, the biggest thing that you have to remember here is to find your positive and negative values when you are, after you take the square root. Because remember, when you take a square root, you get a plus and a minus. So this example right here would be a good place where you would use the square root method because you have one trig function and it's squared. And so our first thing that we're going to try to do here is to make sure that I get the trig function all by itself. And so in order to get the trig function by itself, you just need to divide both sides by that number in the front. Okay, and so I would get that sine squared x equals to 3 over 4. This is the point where you can use the square root. And remember, you have to find the positive and the negative values. So I would have that sine x equals to plus or minus. Remember, when you take the square root of a fraction, you take the square root of the top over the square root of the bottom, and so the square root of 4 is just 2. This is a value that's on your unit circle, and you know special right triangles with this ratio, so life becomes a lot easier. So when I look here, I'm going to go ahead and draw my unit circle, and I'm going to start with the positive values. And so for my positive values, I would go and have my triangle that has the opposite over the hypotenuse of root 3 over 2. Complete your triangle, and you would know that this is a 60-degree angle, or pi over 3. Okay, so your first positive solution would be pi over 3 plus 2 pi n. I know that I'm using radians here because it doesn't say anything about degrees, and they're also using an x. So I'd have pi over 3 plus 2 pi n for my first positive solution. My other positive solution is going to happen in quadrant 2 because all students take calculus, and I would have that same reference angle, but now it's going to be over here. So we would take pi minus pi over 3, and that solution would be 2 pi over 3 plus 2 pi n. Okay, so those are where your positive solutions lie. If you wanted your negative solutions, we just think about those other places that have that same value. So again, my negative solutions and my principal quadrant was going to be down here in 4. So I'd have negative root 3 over 2, and then I still have that side length of 1. So I'm still looking at a pi over 3 reference angle, so I can either write that as negative pi over 3 plus 2 pi n, or you could write that as 5 pi over 3 if you went all the way around your unit circle. Okay, and then last but not least, you have this quadrant 3. It's going to have the same reference angle, but again, you either want to go backwards all the way or go all the way around, and that would be pi plus pi over 3, and so that final answer would be 4 pi over 3 plus 2 pi n. You can't forget your coterminals, and so this would be your final answer for the general solution because they wanted all real numbers for this equation. Okay, so that is generally how you would solve a square by square roots. The next one is combining like terms. This is when you have the same trig function, but they're hanging out on two sides of the equation. So what you need to do here is you need to combine like terms and move over one of these cosines so they're both on the same side. I'm going to move the smaller one, so I'm going to subtract a cosine x from both sides. And so the equation I'm dealing with now is 2 equals, and 3 minus 1 is 2 cosine x. And now I'm trying to get my trig function alone, so I'll divide both sides by 2. 1 equals cosine x. So now in order to get this guy solved, I'll take the inverse cosine of both sides. And so I'm looking for the place on my unit circle where cosine is equal to 1. So you can use your OIO chart, or you can go in here and think about where is x1, and x is only 1 at one point on my unit circle, and that's at 0. So I would write my general solution as 0 plus, and since I'm in radians, I would have plus 2 pi n. And again, having that general solution is super helpful because then if they asked you within a certain range, you could say, here, I'll just keep plugging in numbers until I find those values within the range. Okay, so combining like terms, try to get all of your trig functions on one side, and then isolate the trig function. The next type was the factoring, and there were two different types of factoring. The first one was the greatest common factor, where you looked and you said, what do I have in common here? And you typed it out. And the other one was quadratic, where you were legitimately factoring. So let's start with the GCF method. Again, we're looking for a general solution in radians. So when I look here, I notice that we have a tan x in both of my expressions, so I'm going to go ahead and take out that tan x. And when I say take out, I mean divide everything by tan x, factor it out. So now I'm left with tan x, and don't forget that this is 1. So now I can go ahead and use my zero product property and set this piece equal to 0 and this piece equal to 0. So I'd have tan of x equals to 0 for my first part, and then I would have tan of x plus 1 equal to 0 for my second part. So I'm going to go ahead and start with the blue one. I'm going to take the inverse tan of 0 equals to x. So now at this point, again, you can use your OIO chart, or you can think where is y divided by x equal to 0 on your unit circle. Okay, and there's only one spot where we can have that happen. Well, actually there's two spots. Sorry, I was looking at my notes confused. So if you look at your OIO chart, OU, I remember this is so good, so we're looking for where is tan 0. So there's two places on here where tan is 0, right here and right here. So this is 0, pi over 2, pi, and then 3 pi over 2, struggling. So when I look at this guy, I have those two spots, but if you notice, they're exactly pi units apart from each other. So if you remember with tangent, you are allowed to just write your one solution and then add pi into both of them instead of trying to figure out the two different general solutions. So if you looked at that one thing, you'd notice that these are exactly pi apart, so I don't have to write pi over, or 2 pi n. So again, there's two ways to write it. I'm just going to write 0 plus pi n equals to x is my first solution. Okay, now I'm going to do the other guy, and again, I'm going to isolate my trig function equals to -1, and then take the inverse tan of both sides. It's -1. So right here, if I look on my OIO chart, tan is never equal to -1 on this, but that just means that that is going to be at a real angle and not on a quadrant border angle. So if I was to draw out a triangle, and remember this is negative, so I'm going to be in quadrant 4, I would have an opposite over an adjacent of 1. If I use Pythagorean theorem, I would know that's a 45-degree angle. So I can have that this is negative pi over 4 plus, and remember, you can do 2 pi in, but then you have to find the other place where it's equal to. So if I'm thinking about where is tan negative, it's also negative up here in 2, but I notice that those are just 180 degrees apart, so I can just write pi n equals to x. So my two general solutions would be 0 plus pi n equals x, and negative pi over 4 plus pi n equals x. Okay? And again, you could have 4 different solutions here. You would just have to write 2 pi n in the end. Okay, the other way that we saw this is when we had to factor. We had to legitimately factor this guy. And so if you think about this as these are just x's, this is something that we factored before, where we looked for those factors of 2 times 2 is 4 that added up to be -5. Well, that would get me -4 and -1. So I would go ahead and split that middle term up based on that guy. Oh, and I kind of already split it for you. And now I would find those common factors in here. So that would get me 2x in that first part. Then I would have x minus 2 left. This is where it gets kind of weird. I'm trying to match up my parentheses, so I'm going to subtract 1, or take out a -1, so that'll get me a positive x and a -2. These factors should be left and be the same, and so that's your first factor, and your second factor is whatever's on the outside. Okay, and so what I just did there, remember this is a variable, so instead of using x, I'll just use cosine of theta. So if I looked at this guy, this would be 2, oh, maybe not, it would be 1 cosine theta, so cosine theta minus 2 times 2 cosine theta minus 1 equals to 0. So you can factor this one of two ways. You can look in here and you can pick and call this a different letter and just factor it like you would have done in Algebra 2, or you could have just used cosine theta and figured out those same numbers. Once you have this piece though, you are welcome to set each factor equal to 0 and solve. So I have cosine theta minus 2 equals to 0, and then I go through, I add 2 to both sides because I'm trying to isolate my trig function, and then I would take the inverse cosine of both sides. Okay, again, when you look here, you would think about that triangle that you could make that has an adjacent side of 1 and a hypotenuse, sorry, an adjacent side of 2 and a hypotenuse of 1. This guy doesn't exist. Okay, that doesn't work out because I can't have a leg that's longer than my hypotenuse. So this guy does not exist. So hopefully we get something that works on the other side, otherwise I have no solution to this equation. Okay, so I would have 2 cosine theta minus 1 equals to 0. I'd add 1 to both sides and divide by 2 just to isolate my cosine. And this one does look like it's going to work out better because I know there's a place on my unit circle where cosine equals to 1/2. So I have the inverse cosine of 1/2 equals to theta. And so now I want to think about on my unit circle, where is this true? So positive cosine is going to happen in quadrant 1. So 1, sorry, I drew that as a sign. Oh no. So you're going to have your adjacent side be 1, your hypotenuse 2, so this is root 3. And that would get me a reference angle of 60 degrees. If you look at your domain here, this says x, it should say theta. Theta is all real numbers degrees, so I'm looking for a general solution in degrees. And I also know that because it's a theta. So I would have 60 degrees plus my coterminal for this one would be a full rotation of 360 times n. So that's my first general solution. Again, I got to think about where else is cosine positive. All students take calculus, so down here in quadrant 4. And I know I can do this two ways. I could write this negative 60 plus 360 in, or I could go all the way around and write 300 degrees plus 360 in. Okay, but I'm just going to write negative 60 because I'm lazy. And since all they wanted was a general solution, we're good. So it's factoring. You either have to take a greatest common factor of both, or you have to factor out using that. You can use the X box, you could use the grouping, all those methods. The last one is the one we've been doing a lot. It's trig identities. So what you're looking for here is you're trying to make this all into one trig function, and this is where you want to use your formula chart. So if you notice there's a lot of stuff going on, or you see different numbers like you have 1 minus 2 cosine squared x, or you have sine of 2x, or you have something crazy going on, two different trig functions, you can't take out a common factor here because there's nothing that has the same argument. So you're going to run to your formula chart and see if you can find anything that matches here. So when I look right here, I notice that these two guys match. So this would be my A, and this would be my B, and I'm going to have a sum or difference property. So this is on the front side of your formula chart. So if I look on here, since it's a sine cosine, this is going to be sine of A, and then I look this sign is a minus, so looking at my formula chart, I'm going to subtract my B, and that equals to negative root 3 over 2. This is much more straightforward. This is sine of 2x minus x is just x, and now this looks like stuff I've been doing in the past. So I can just take the inverse sine of both sides and then find my general solution. So again, the idea here is to not make this any harder than it has to be. So find out if you could simplify your expression at all. So the first place where sine is negative, the principal value is down here in 4. So I'd have root 3 over 2, that gets me 1 right here, and my degrees, my reference angle, would be pi over 3. So I can write this as negative pi over 3 plus 2 pi n for that coterminal. And then I go find the other place where sine is negative. All students, those are both positive, so I must be down here in 3. Same reference angle, so that reference, or that angle, that entire angle would be pi plus pi over 3, or 4 pi over 3. And we could have written my first angle, we could have written that as 5 pi over 3. Okay, and I knew I was supposed to be in radians because I have an x here and it told me all real numbers, so I just want the general solution, and that's it. So the big thing about trig identities is to just use that formula chart, look and see if there's any way I can simplify craziness that's going on, especially if you see two different trig functions going on. And once you get it all in terms of one trig function, take the inverse of both sides and move on with your life. All right, I hope this helped you out if you needed some extra help solving trig equations, and I will see you tomorrow.